Hi, I'm Sannel with Pinnacle Ozone. I want to thank you for joining me today. This presentation is part of our Pinnacle Academy series, where we bring ozone to people in a way that's clear, accessible, and informed by real-world examples. In this session, we'll take a closer look at how ozone is produced, how it behaves, and how it is applied into actual wastewater and water treatment systems. We'll also explore the chemistry, the equipment, the process design, and the performance matrix that matter most. Whether you're new to ozone or you've worked with it for many years, my goal is to give you a technical understanding that's practical and proven, based not just on theory, but what we've seen in the industry. Thank you again for being here. Let's get started. So here's a quick overview of where we're going in this session. We'll start with the basic chemistry of ozone, what makes it such a strong oxidizer, and then walk through how it is generated and transferred into water. From there, we'll look at oxidation reactions, the system components required to make it actually work, the instrumentation and monitoring equipment that will play an important role in the safety and efficiency of how we get ozone into the water. And then finally, we'll wrap it up with a real case study where we'll look at the ozone system and see how it translates into results. Each section will build on the last, so whether you're designing, operating, or just learning, you'll get a full picture of how an ozone system is made. So let's begin with the molecular structure and the behavior of ozone. So ozone is composed of 3 oxygen atoms, O3, arranged in a bent polar structure that has an internal bond angle of 117 degrees. The polarity gives it a highly unstable, reactive nature. It's constantly trying to react to be more stable in terms of the O2 configuration. This makes it such an effective oxidant. Its standard oxidation potential is 2.07 volts, which is higher than chlorine, hydrogen peroxide, and chlorine dioxide. This means that ozone is capable of oxidizing a wide range of contaminants, including many that are resistant to your conventional disinfectants. Ozone has a half-life in water about 15 to 20 minutes under ideal conditions. But in most environments or most field environments where we see temperatures, pHs, and organic load vary, you will see it shorten depending on what the variabilities are. That short half-life is actually beneficial in many applications. It means the ozone is going to react quickly, it's not going to persist in the system, and it's going to break down naturally into oxygen, leaving no harmful residue. Now that we understand ozone properties, let's look at how we actually generate it. Most industrial ozone systems use a process called corona discharge. This involves passing high voltage alternating current between 6,000 to 15,000 volts across a narrow gap between 2 electrodes. That gap is separated by a dielectric material, which prevents arcing and creates a controlled plasma field. In that field, molecular oxygen, O2, is split, and this causes individual oxygen atoms. Those atoms then recombine with another O2 molecule and forms ozone. This process happens continuously as the oxygen flows through the system. The voltage is very high, but the current is low, and the system runs at a very high frequency, usually between 20 to 30 kilohertz, to maintain high efficiency and avoid instability of the plasma. One of the most critical factors in ozone generation is the feed gas quality. We cannot run ambient air through the ozone system. It contains moisture, it contains nitrogen, which actually reduce the ozone yield, which can form nitric acid, and this actually damages internal components. That's why we use dry, high purity oxygen that can either be created by PSA, VSA systems, which I'll talk about in the next few slides, and liquid oxygen. We also cool the cells continuously. Heat is a major enemy of the ozone production. It reduces the conversion efficiency and can actually accelerate ozone decay. So therefore, we actually cool the ozone cells down to produce a higher efficiency of ozone. This results in a clean stream of ozone-rich gas, typically between 6 to about 12% ozone by weight, which can then be injected into the process stream. Once the ozone is generated, the next challenge is actually getting it into the water and making sure once we have generated it to actually inject it into the water efficiently. That's where the gas to liquid mass transfer comes in. Ozone has a moderate solubility and has a half-life which is pretty short. So we have limited time to get that ozone into the water and actually reacting. The goal is to achieve a high efficiency, typically between 85 to 95%, meaning that most of the ozone can be injected into the process. Mass transfer or the transfer efficiency depends on a few factors. One being the bubble size. The smaller the bubble size, therefore you have a larger surface area for absorption. The contact time, therefore you have enough time or enough residue time for the gas to actually dissolve and react. And then turbulence and pressure. This helps drive the gas into the solution. The method that we choose for injection depends on the size of the system, the flow rate, the water quality, and most of all the time that we have. We use Venturi injectors. These create a vacuum that pulls the ozone gas into the water stream at high velocity. They're reliable, self-cleaning, and there are no moving parts. The mass transfer is one of the most overlooked parts in the ozone system. It is absolutely critical. Poor transfer efficiency wastes energy and more wastes ozone. And that's the main benefit of using an ozone system, is to make sure you're generating and injecting it into the water correctly. So this is where ozone earns its reputation, through the oxidation chemistry and the disinfection kinetics. Ozone operates in two modes. One is direct and one is indirect oxidation. In the direct oxidation, ozone molecule itself reacts with contaminants. It targets electron-rich sites such as phenols, iron, manganese, sulfates, and certain organic compounds. These are fast reacting and they are relatively selective, but immediate reaction takes place. The second module, or the second mode, is indirect oxidation, which occurs when ozone decomposes into water to form hydroxyl radicals. Especially at a higher pH level or in the presence of certain catalysts, these radicals, denoted as OH negative, are far more reactive and less selective. They will react with almost any organic molecule that they encounter, and this will make it more efficient. This is a process that we call AOP, or advanced oxidation processing. To put this in perspective, the rate that ozone reacts with the phenol is about 1.3 million per mole per second. The same reaction with the hydroxyl radical is 5,000 times faster, 6.6 million per molar per second. Ozone reacts quickly with metals like iron and manganese, converting them into insoluble forms that can be then filtered out. Ozone also can disinfect and get rid of any bacteria. You can achieve up to a 4 log reduction with the 1 ppm concentration, which is significantly greater than chlorine. So whether you're targeting pathogens, reducing BOD, or removing iron, or looking at treating sulfur, ozone's reaction speed and versatility make it incredibly efficient, especially when the system is designed to promote both direct and indirect oxidation. So let's walk through a full ozone system, what it actually takes to build a reliable, high-performing ozone system. This is where ozone moves from a chemistry side of things to more of an engineering-based study. So first of all, we start with the feed gas. We either use PSA or VSA. I'll explain those a little bit. So PSA is pressure swing absorption. VSA is vacuum swing absorption. Or you could use liquid oxygen, depending on the application size and how much oxygen is required. It depends on which you select. But what matters most is that the oxygen is clean and dry. Moisture and impurities will reduce the ozone yield, but will also start affecting the ozone generator. PSA units typically produce about 93% oxygen, while liquid oxygen produces about 100%. Next is the ozone generator itself. This is where oxygen passes through the ozone generator. This is where corona discharge occurs. High voltage AC current splits the O2 into different oxygen molecules, where then it reacts with another O2 to form O3. This is where ozone is formed. This process is sensitive to temperature, gas pressure, electricity, so the system must be very precise and cooled as well. Pinnacle systems are built around the plasma block technology that maximizes the efficiency and increases reliability. After the generator, we move into the ozone injection system. This is where the mass transfer stage happens. This is where the gas is dissolved into the water. Depending on the water flow and application, we use a Venturi injector or a diffuser stone depending on what type of application we're looking at. The goal here is very simple. Get as much of the ozone into the water as possible. We are looking at 90% efficiency and greater. Getting as much ozone into the solution is the most important, and also getting it there quickly is important. Once the ozone is into the water, it enters a contact chamber. This is where actually oxidation and disinfection occurs. Designing here is critical. You need the right CT value, you need to make sure that there's the right retention time, and you need to make sure that you're actually getting the ozone into the water. If you take a shortcut during this step, you will lose the power of ozone. Any undissolved ozone gas is then sent to a destruct unit. This prevents any releases to the atmosphere and makes sure that the operators are protected. We use either a catalytic or thermal destruct unit. It depends on the volume and size of the ozone system and the site conditions. These are sufficient and safe ways to convert the ozone back into oxygen. Throughout the system, we rely on instrumentation and automation. Inline dissolved ozone meters are actually used to measure the ozone concentration in the water. The ORP sensor is used as a secondary sensor to actually look at the amount of oxidation reduction potential in the water. A PNID loop is used to control and maintain the dosage in the water based on the flow and the water quality. Safety interlocks and gas detectors are used to ensure that we stay below OSHA limits. In large systems, we may also include recirculation pumps, multi-injection points, and this helps balance the amount of ozone that we want to get into the water and maximize the efficiency taking place in there. The takeaway here is that for a successful ozone system, it isn't about just the ozone generator. It's about every single piece, from oxygen prep all the way through the destruct unit. It's all engineered together and make sure to work together. Reliable ozone performance depends on real-time measurements and control. The chemistry moves fast, so the system needs to move fast as well. The most important parameter we monitor in the water stream is the dissolved ozone concentration. This tells us exactly how much ozone is in the solution and actually is active. We either use a UV analyzer or a probe depending on the system scale and the water quality. Many systems also include an ORP sensor as a secondary indicator. The ORP, once again, is oxidation reduction potential. This gives us a broader view of the redox environment, but is less precise for ozone usage. On the safety side, we also include an ambient monitor sensor that detects the ozone level in the space around, and it will trigger alarms or even shut down the ozone system if it goes above the OSHA limits of 0.1 ppm. All this data that we collect from the sensors and the monitors is passed into our PLC. Our PLC, so just to give a nomenclature to PLC, is a programmable logic controller. This is what runs the system. If you want to think of it as the brain of the system, most of Pinnacle's systems use a PNID control loop. This means that it's automatically adjusting the ozone output based on flow, temperature, and the parameters that have been put into the system. The control system also handles event logging, alarms, automatic shutoff. So if the ozone level drops, or the dissolved ozone level drops, or sudden flow changes, the ozone system is able to respond to that. So that's what we call a PNID control that actually can control based off external parameters coming in. The level of automation allows automators to focus on the process, not babysit the equipment, while still maintaining tight performance. Our whole idea behind a smart PLC or smart system is to ensure that the system reacts to all the fluctuations that come along. We spoke about OSHA levels, we spoke about safety, so I wanted to touch a little bit further in about safety and regulation compliance. With ozone, safety is not optional. It's engineered into every part of the system. Ozone is a powerful oxidant. While it is efficient in water, it can be hazardous in air if not controlled. The OSHA permissible exposure limit for ozone is 0.1 ppm, which is average over 8-hour workday. For short exposure like 15-minute period, the recommended maximum dose is 0.3 ppm. Even at low levels, you can start having an irritation, so we don't want to take any chances. That's why every system that we include or we install, we always include an ambient ozone monitor. These continuously check for any gas that escapes into occupied spaces, or if we detect a leak that's above the threshold, the system will trigger an automatic alarm and would initiate a shutdown process. We also design for zone isolation. Critical components like the ozone destruct are interlocked with the generator. So if the destruct unit isn't functioning properly, the ozone generator won't run. Enclosures are completely air sealed, and air handling systems are also designed to make sure that we can manage the ozone off gas safely. On the ozone destruct side, we use either a catalytic or thermal destruct unit, and this is used to destroy any excess ozone that's left over. The catalytic destruct units are energy efficient and are suitable for higher flows. With thermal units, you're looking at higher concentration, especially where the gas volumes are significantly higher. All of this is monitored and controlled using the PLC and is reported. Therefore, makes it very easy for compliance audits. The goal is very simple: maximum performance with minimum risk, both for the process and for the people operating it. So, as I said, we're going to look at a case study here. I wanted to highlight a real-world example so you get an understanding of how ozone is used. So, let's look at this example. This is Sherbrooke in Quebec. They're drawing from a river. They had a legacy ozone system nearing the end of its life. They needed something reliable, efficient, and easy to maintain. We installed 3 Zenith 20X ozone generators, each producing 5.3 kilograms per hour, and designed the system to run with 2 units operational and 1 on standby. The modular setup ensured that we have redundancy built in, with a 15% capacity if we wanted to expand the ozone system. One of the standout features is the ozone on-demand control. It controls and adjusts the ozone output in real time to match the water quality and the flow. That means the ozone generators are always producing 10% ozone by weight, even as conditions change. What did Sherbrooke see? We reduced the amount of energy that was used, we reduced the amount of maintenance that was required, and we lowered the operator workload. This was a complete bundle that they requested. the system has exceeded expectation in reliability, cost savings, and ease of operation. This is not just theory that we're throwing out. This is what we've actually measured the improvements at the location. So in this section, I want to provide you a little bit more on the ozone cell itself. So what makes Pinnacle systems versatile? These are the principles that are constant across industry, across any type of industry when you're looking at industrial or municipal design. So firstly, the systems are built with simplicity in mind and reliability as well. Each subsystem, from oxygen delivery to the injection to the destruct unit, is optimized for doing its function cleanly without any additional complexity. Fewer components means fewer failure points, but also lowers the maintenance demand. Systems are designed to produce high concentration ozone, typically between your 8 to 12% range, and this improves the efficiency of how you get the ozone into the water. The systems are designed to produce high concentration ozone, typically between 8 to 12% by weight. This improves transfer efficiency and lowers the total gas flow, which therefore decreases the energy usage. Output remains stable across a wide range, which is critical for variable flow processes. Integration is another key aspect. Units come with a built-in oxygen preparation system, smart processing control, and full safety turnkey system. This reduces the need for external systems and simplifies installation and operation. The plasma block generator has no moving parts, which eliminates mechanical wear and minimizes maintenance. Energy efficiency is high, and the ozone production is constant over long periods of time. Remote monitoring and control features are built in, enabling continuous performance tracking and fast responsive to alarm and process changes. All of these design choices are intended to support long-term operation stability, especially in environments where reliability is critical and resources may be limited. That concludes this technical overview of how ozone works. From molecular properties to a full system integration and real-world example, we have covered all of this in this presentation. If you have any questions or if there's something you would like to learn more in depth, please feel free to reach out to us at info@pinnacleozone.com. Whether it's about chemistry, system design, or just application, the team is here to help. Additional learning modules and resources are also available through Pinnacle Academy to support continuous training and a deeper understanding. Once again, thank you for being part of this session and taking the time investing in your ozone knowledge. Thank you.